All right, it's probably time to resume our workshop. There are many interesting questions in the chat. I think some of them deserve some attention before we move to the next point, especially considering the issue of weights that Annette raised before. So maybe Annette, I can say something and you can follow up if you have something in addition. The issue of weights is a bit critical here because it really depends on the data structure you are dealing with. This means that, for example, if you have panel data on a cohort, on a specific birth cohort, probably the weights for the individuals on the first time point is reliable in terms of representativity of that cohort at that time point. And that's the easiest way, I would say. But there are other cases where you construct sequence data, and we will see an example in the hands-on. And individuals enter the sample at different ages, at different time points along the survey data collection. And therefore, it's harder to understand what weights we are really need to use to generate a representative sample of something. So that's an open question in the sequence analysis community at this point, because it really depends on what your focus is and why you want to use weights, whether you want to generalize to the population in a country or to a specific cohort or to the population at a specific time point. And there are some data limitations that you have to face. So there's no yes or no answer to the question whether we have to use weights. It's probably a good idea to use them if you are able to understand exactly what those weights lead to. So what kind of representativity you reach when using the weights. And in some cases, actually the weights are a bit of a mess and you don't really understand what you are bringing your sample to what population. And therefore, given that we are still talking about a descriptive technique here, it's better to have a good description of something that is not affected by this weighting schemes that are not necessarily helping us understanding what those processes look like. I don't know, Annette, if you want to add something to this. Okay.
Oh, that's fine. Go ahead.
All right. I think I will start sharing my screen with some slides that introduce the hands-on. And then the hands-on will basically reproduce many of the things that we will see on the slides, but it's useful to have a first overview so that then you can orient yourself when we move to R. So. All right, so in this part, I'm going to introduce very briefly the data we use for the hands-on. Remember that you should be able to access the data and the code we're going to use via the web page of this workshop. And then we'll see how to define and describe the sequences within the R environment. And we talk a bit about visualization. So first about the data. The data we're going to use consider family formation trajectories, and these are from the German family panel, the PERFAM data. Maybe some of you are familiar with that. This is a great data source. It's a couple level data set. So for those who are interested in looking at couple level dynamics, that's a very nice data to consider. If you want to know more about this data, there are plenty of references also in the Outlook we shared for the course. I want to say that the data we're going to use are not the full data set, but is like a 40% sample of the initial data. And that's why we can distribute it to students or individuals who attend this course. If you want to use the data, it's free of access, so you just have to apply it to the PERFAM website. What is the data format that we need for starting working with sequence analysis in R? Well, at this point, you know that the main packages are Traminer and Traminer extras in R. And for these packages, what is required is what is called a wide format. So we need data to be organized in rows. Each row represents an individual. And for each individual, we have multiple observations that are reported as successive columns in our data. And for each column, there is an indication that refers to the alphabet of the states we are going to use to, let's say, build our sequences and then conceptualize those sequences as individual trajectories for a specific temporal process. So in the example here, we have two individuals and we have 7 time points, which we name from state 1 to state 7. And the first individual starts in state 1 in being single, and it remains single for 3 time points, and then moves to LAT, living apart together, life arrangement, and then stays in this state for 3 time points, and eventually get married at time point 7. Something different happens for individual 2, and this will be the same for all individuals in our sample. And the important thing here is that we retain the information that we need a wide format that refers to multiple rows, 1 per individual, and multiple columns, each referring to a time point, which is coded according to the state in which that individual is at each time point. Regular data from panel surveys can be easily prepared for sequence analysis. When I say easily, it really depends on the initial state of the data. In some cases, it's easier because there are some routines that data providers offer you. In some other cases, the work is a bit harder, but it's also one of those things that at least I enjoyed when I started to use these methods. So if the data correctly formatted, Traminer can handle both this data structure that, as Annette showed you before, account for both the states and the time into each state, but also episode data. We are focusing on one specific temporal process here. We look at family formation trajectories from age 18 to age 40. Luckily, we didn't have missing information when we started to build this data. Annette anticipated that if you find that in your data there are some gaps in the temporal process you're looking at, you will have to handle this one way or another. But also, the way to handle missing really depends on how many missing you have in your data, how many individuals present missing, and so on. So also in this case, as for the weights, there's no yes and no answer to who should be retained in the data or how you can handle the missing. It depends on how your data look like. And here in our case, we have sequences of equal length. So we have, for all individuals, the same time points observed. How we start, define, and describe the data we have stored in our initial data set. Well, first of all, we can input into Traminer different data formats. I said that the necessary format is the wide format, but in case you want to impute it in a wide format, you will have to perform some operations to reshape the data the way it's needed. Also, to reassure some of you who raised the point of maybe R not being very much user-friendly, I started to use R specifically for sequence analysis. So generally what I do is to do my data management in Stata because I learned before to use it and I'm quicker in doing that. And then I move to R just when I have to do sequence analysis related things. So it's flexible in this way, and you don't need to be proficient in R to be able to approach the Traminer package at first. Here we are learning about the very basic function that you will need, that is a secdef function. And this is the most important function that you will learn about today, because it allows us to define different data points for each individual as sequences in the Traminer environment. To do that, we will have to specify different things, the label of the states, the colors we want to attach to each of the state and so on, but we'll see this in practice in a bit. About the alphabet and the time points, let's say the level of the time you are looking at, which is called in the sequence analysis jargon this granularity. There are some commands that you can explore further to recode states that are present in your initial data, but you want to, for example, merge or combine. And you can do it in the R environment. I'm not going to go into these details very much, but I want to let you know that these are options. And besides the functions that we are going to look into together, the Traminer package is very rich, is extremely rich, and most importantly, compared to the SQ packages in Stata, Traminer is constantly updated because the community that works on the programming of the package is very active and like keep things going as papers come out, as new propositions are made, etc. So let's start to describe our sequences. So Annette showed you already some figures, and we will go to that in a little bit. But we can do many things with sequences, not just look at how they look like. We can also extract some summary measures. For example, we might be interested in what is the time spent in different states and how likely are episodes to occur along the temporal span we are looking at. So this can be done relatively easy with some basic commands that are the segment by specifying different things in the options. So you will see here in this first line of code that will become familiar to you very soon, that we specify the function, and then we plug in the sequence object that we previously generated with the secdef function. And we ask Traminer to extract something out of this object that is made of different sequences, all defined as such. And what we can do here is to ask for the mean time spent in each state, for the standard deviation of that value, or the relative frequency of that state in our data. So for example, here for this reduced number of states, single, LAT, cohabitation, and marriage, we see that on average, in our sample, individuals spent around 72 months into singleness, on average 48 months as LAT, and on average 59 months in marriage. So this tells us something about the full set of sequences we are looking at, giving us already a hint of how this process looks like. So it seems that time spent in LAT or cohabitation is pretty much the same. So we can argue already that for most of the life course we are looking at, people are either single or very likely to move directly into marriage and stay married for a long time. We can also extract the number of episodes, as I said before. So here, Annette introduced the difference between state and episodes. Episodes are the succession of the same state over time. But here the point is that individuals spend at least one time point into singleness or LAT or cohabitation. And this happens on average 1.6 time for singleness and so on and so forth. So these are summary measures that we can already get very easily out of our initial set, just by looking at one function, the segment, and specifying the secdss function further. We can also explore the number of transitions. This is very important when we want to have a sense of what happens over time. And here, the message for this slide is that depending on the granularity you're focusing on, so whether you have monthly data or yearly data, this picture might look very different. So in our case, when we look at the number of transitions using the sectrans_n function, we see that focusing on monthly data, we get an average of 5 transitions between any state. Because of course, monthly data means that for each year, we observe the same individual for 12 months and so on for each year in our sample. So the likelihood of observing transitions is higher compared to the likelihood of observing transitions with yearly data. In fact, here we only have 4 transitions on average when looking at yearly data. Is this important? Yes and no. Depends on your research question, depend of how frequent certain states are in your data, and whether it's important for you to emphasize the occurrences of transitions at very fixed time points, or you rather want to have a like more of bird eye perspective on the process. Of course, transition happens in specific rates. And in this case, we can extract this information, again, relatively easily from our initial set of sequences. Transition metrics can be interesting, especially in our case when it comes to yearly data, for example. You see here the disadvantage of looking at monthly data, because when I look at the transition metrics in monthly data, and I have 260 something time points, of course, the transition from one time point to the next is likely to be in the same state. So it's not very telling to know that the transition probability from being single to being single is very high and is probably the most likely transition, simply because we have many time points. This becomes a bit more telling when you look at years. But most importantly is probably what we can extract from looking at episodes. Not because time points are not interesting as such, but because looking at episodes instead of states give us a bit more of the sense of what happens when moving from one state to the next. So here in the bottom part of the table, we can see that the likelihood to move from singleness to LAT is 0.42. And the likelihood to move from singleness to cohabitation is actually a bit smaller. Again, from this picture, we can start thinking about what the general process of family formation look like in our sample. All right, I think I'll skip this for now and move to visualization. You might have recognized.
Yes. Sorry to interrupt just briefly. There were a few questions for the data. I said once you get to the actual code, you will walk people through opening the data and so on, right?
Yes,
so
yes,
now,
absolutely.
Everybody should just, we are basically walking you through things before you do them yourself. So for now, you can just focus on what Emanuela is saying.
Yes. Yeah, about visualization. As you might have recognized from the figures that appeared in Annette's presentation before, visualization is a large part of how sequence analysis can actually help you understanding what's going on in this process over time. So it's important that you understand the right way to visualize things depending on the features of the process you want to highlight. You can inspect the data in different ways, and visualization is the prominent way we want to inspect our sequences because the set of sequences we generally look at are very complex objects. So Annette gave you a good example at the beginning. If I only have two sequences, I can easily identify the differences between them. But if I have 1,000 sequences, I cannot do it easily, like in the same way. So I do need some simplification for visualizing the set of sequences in a way that give me a sense of what's going on. The tabular representation we have seen so far can be interesting for some specific aspects, but in most cases, the information doesn't really give us a sense of what happens over time, which is exactly what we want to achieve by using sequence analysis. Here we are looking at two types of graphs, which we call data summarization graph and data representation graph. Data summarization graphs help us aggregate and summarize the information that is stored in the sequences, and data representation render directly individual sequences instead of aggregating summary measures over time. Also in this case, there's no right or wrong. It depends on what you want to learn about the temporal process you're looking at. One important thing that I want to highlight is that given that visualization is so important, it's also important that you spend a little bit of time choosing the colors you are going to attach to each of the states you use to define your sequences. This is not a trivial issue because visualization is what will guide you interpreting the substantive information that you can extract from the sequences. So depending on the colors, you might help your reader and also yourself to learn more about the process you're looking at. You have several options there. R is very rich in this sense. We will generally use this color brewer package, but there are other options you can explore. And I really encourage you to spend some time doing this for yourself. So let's start with the data summarizing graphs. One very important graph in this respect is the modal state plot. Here I display let's focus on the left-hand side of the slide now. I display the modal state plot for men and women in our data coded as 0 and 1. And you will learn in a bit that it's very hard to manipulate these figures in Compiler, unfortunately. So these are for men and women. And on the y-axis is the frequency of each state in our alphabet over the time point from 1 to 260 something, which is our months on the x-axis. So you see that here I use a bit more complex alphabet from single, no child, single with children, LAT, no child, LAT with children, cohabiting with and without children, and married without children with 1 and 2 children. So what happens here? That the plot displays the share of individuals being in the most frequent state at each time point. So that for the left-hand side of the figure, we see that at age 18, which is represented by the beginning of our time frame here on the x-axis, at age 18, around 70% of the individuals that are men in this case are single. And then the modal state remains the same because it remains being single, but the share of individuals being that state decreases over time. And then at some point there's a twist and the modal state changes to married with 2 children. And the share of individuals being in this modal state increases over time. As such, this information is interesting, but it's more interesting if we compare it in the other group. So among women here, they do start being single as a modal state, but this changes relatively quickly and they enter cohabitation at some point and cohabitation becomes the modal state. So the most frequent state in our sample. The same as for men applies to women here. At some point there's a twist and being married with 2 kids becomes the modal state and the share of individuals being in that state increases over time. So we can learn already something about this, not just about gender differences in the process, but also about the states that are most frequently experienced by the 2 groups. I mentioned before that labels here are a bit difficult to manage in R. On the right-hand side of the plot, I show you an alternative representation where we could reproduce nice labels, and we offer you the code for doing that, so you can explore it a bit more yourself. Another very important summarizing graph is the state distribution graph. What does this show? It shows at each time point where individuals are in the full sample. So it means that for age 18, represented here with state 1, we have around 60% of individuals being single, and another 30% of individuals being in an LAT without children. This graph is very interesting because it shows the relative frequencies of each state over time. So we can have a sense of where our population goes over time. So mostly from being single or in a LAT relationship to being in a partnership of different kinds, and in most cases with at least 1 child. So this is a very important information we get from this state distribution plot, which however gives us a representation of what happens in the full sample, so the full population. Why it's so important to distinguish between state distribution and what we will see later that is called index plot? Because the state distribution plot that we see here on the extreme left side of the figure might arise from different individual sequences. So as I said here, we have a picture of where the population goes, but it doesn't mean that everybody is in that state where we see the majority of them at the end of the process. So it means that the same distribution plot can arise from different sequence index plots. The sequence index plot instead is already one of those sequence representation plots. So it represents individual sequences. And from different index plots, we can get the same distribution. Why is this important? Because for arguing something about how the process look like for individuals, we really need to focus on the index plot instead than on the state distribution plot. For example, here, let's look at the sequence index plot 1. If we want to interpret generally what happens here, we can probably argue about the fact that in most cases, people move from singleness to either being in a cohabitation or marriage. But if we look at the sequence index plot 2, which leads to the same distribution plot, we might have to say that actually most individuals remain in either single or LAT at the end of the process. But this is something we might have confused just looking at the state distribution. So what we recommend is to combine information from different kinds of plots. One final graph I want to introduce before moving to the hands-on is the relative frequency sequence plot. So the standard sequence index plot presents a major risk, which is overplotting, especially when you have very large samples. So normally index plot can stand okay with 200 sequences. When you have more than 200, theta or R start to overlap initial sequences displayed to new sequences that need to be displayed. This is a disadvantage in the sense that actually we don't really know what we are looking at because some of the sequences are hidden behind others. So Annette and Tim Liao came out with a very clever proposition, and instead of showing all the sequences in the sample, they suggest to identify some representative sequences instead. So some representative sequences that help us summarizing already some of the complex information that comes from the sequences. The procedure is very simple, but you don't have to perform it yourself. There's a specific command to that. So sequences are sorted. After sorting the sequences, these are divided in equal groups. And then one representative sequence is extracted from this groups of sequences, and we will only display that representative sequence. How does it look like? So here we are looking at the sequence representatives, which in this case are medoids, and I'm going to introduce this concept later. Sequence medoids for the full sample we have in our illustrative data. We have around 1,000 something cases, which is not very nice to be displayed in sequence index plot. So with the relative frequency sequence plot, we can select some representative sequences and display them instead of the full sample. What comes together with the relative frequency plot is a second graph that we see here on the right-hand side of the figure, the dissimilarity to this representative. This is very instructive because it tells us not just what are the representative sequences, but also how representative they are. So if we look at the top sequence here, we can, I know that these are individuals who are married with kids for mostly the largest part of their life course from age 18 to 40. And this one sequence is very much representative of the small group it is representative of. In fact, the dissimilarity to the medoid that we see here on the top is very small. So the largest the value, the largest the dissimilarity. This means that this sequence is very representative of those sequences in the group. Is this an important information? Well, it is, because, for example, it says that those guys here are very similar to each other, those in that group. As we move to the center of the figure, we see that this similarity increases a bit. It means that these sequences are representative of the groups, but in the groups, there's a bit more variation. And we will learn in a bit that the variation within our pool of sequences is actually what we are interested in, because we want to measure that variation. We want to identify how different sequences are. Also, in this case, there's a command to do to render this plot in R, which is the secplot.rf. And we will see in a minute how to work with that. So now you have a general picture of what we are going to explore with the data. If you downloaded the folder from the course webpage, you should be able to see somewhere on your machine this combination of subfolders. One with data, one with code, figures and tables, which should be empty. And then for part 2, you have this SA_part2 rproj. What we're going to do now, and I start on my machine from scratch, so you will see how it works.
Yeah, while we wait for this, are there any more questions we can address?
I have a question actually about a little ways back. Oh, sorry, a little ways back in your when you were looking, I think the modal graphs. I was there was like some gender differences, and I'm like, how could, given that most couples are heterosexual, how do you end up with like these very, very different looking patterns?
That's a very good question. Thank you for raising it, because Annette introduced this concept of where do we want the sequences to start? And there are different ways depending on what your research question is. Here we are looking at historical time. No, we are looking at age. And we know that in heterosexual couples generally couple with a different age group person.
Yeah, the men are usually a little older, right?
Like on average in the population. So it means that if we have this perspective that construct sequences based on age, we will look at age differences. Of course, this and another very good example for this. If we look at employment trajectories, and we looked at, and we know that individuals exit the educational system at different ages. If we stick to the age perspective to build our sequences, what we're likely to find is age differences that are related actually to when people exit education. So if we really want to know what happens after people exit education to enter the labor market, we might want to restructure your data and align the sequences, not according to age, but to the first year after exiting education, for example. And to go back to your question, what we see there is not gender differences as such, but rather age differences at first significant relationship, if you want to say so. So
that's the age differences.
Go ahead, Annette.
Oh, sorry. And then I think some differences in repartnering, some gender differences in the repartnering, and that the women end up single mothers more often.
Got it. Okay, well, thank you.
Sure. So I'm not sure we can move to the end zone now. Paul, is there? Well, if materials are not there, I would say it's not super bad. I can walk you through the material, and you will try yourself and come back to us via email for clarification questions. Okay.
Wait, we have another. I think then maybe let's wait until it's online.
Okay.
If it's in a few minutes, then people can follow.
So there's a question on transition rates and number of transition rates and numbers are different between monthly and yearly data. I was wondering if identified partners could be different as well, depending on time interval. They might be. In our case, not much, because basically the yearly data are a summary of what happens in the 12 months that belong to that year. So I will show you in a bit when we can look into the actual data, that we start from monthly data and then we tell Trominer, well, we don't really want this granularity. I want to generate yearly data. So just pick the most frequent state among those 12 and code the year according to that state.
And the reason is here also with the family formation, people usually don't switch between being parents or non-parents or married and not married on a monthly basis. So I think if you have labor market employment trajectories, and for example, the NLSY data I showed you earlier has a very detailed monthly account of their work trajectories. And here we find a lot of variation also on a monthly basis, and there it would be important. But family formation, often if you have it a quarter yearly can be a bit crude. So, but quarter yearly usually captures most of the relevant temporal variation. But this really depends then on the process you're looking at. Yeah, then we have another question here about costs. You probably mean optimal matching. We will talk about that in the part after the visualization, which ones to use, and also have some references with some guidelines on which ones to use, but we'll talk about those choices a bit later. More generally, it's really a pity that this is online and we are not there. It's quite different, and also that we cannot learn more about your backgrounds. We agreed in the beginning with Paul, and now with so many participants, it probably would not have been feasible, but it's really too bad. We don't know more about you. I assume we have a lot of demographers here interested in population processes and health. But yeah, if you have specific interests on areas or applications also, please ask questions and let us know how we can target a bit more towards your prior knowledge of sequence analysis and your interests here.
Maybe what I can start to do is to give an overview of how the R environment look like for those who are not familiar with that. That might be something we can invest some time with.
Yeah, that's a good idea.
All right. So here is my R environment. What's important to us today is this window on the top left, where we have our already prepared script, which we're going to run together. And on the bottom left, there's the console, which will display some of the results we are going to produce. Not just the results, but also will keep track of the commands we run. Now my environment here on the top left, right, sorry, is empty because I didn't load anything yet. I just opened the part2 project. And what we see here on the top right, which is the part that is going to like change very frequently, now is containing the files that belong to this part2 of the ends-on. And here we have the SA_part2R, which is the code that I have displayed already here on the top left. And then two additional R code. One is the load install packages, which was already in session 0, we distribute in advance. And then there's another that I call nicer modal plot. I promise you to share this code for a nicer modal plot, in fact. I leave it there for you to give it a try and produce it yourself with the data we distribute. What happens here on the top, on the bottom right, sorry, is also that we will see some plots appearing in the plot sheet here. There's nothing now because we didn't try to plot anything. And then most importantly, the packages that are already installed on your machine, but not loaded. And then the help page. So this is your support when working with R. You can ask to the help how the commands work and learn more about each command. So many of the commands we're looking at today are actually much more richer than what I can explain in this few minutes. So whenever you will start your own project, you really want to look into the different features of the commands in the Traminer package. For example, if I here type Traminer, it will not appear because it's not a command, but secdef, which I mentioned before. Well, I didn't load anything, so R will tell me all the secdef or similar to secdef function that exists in all packages, and I recognize it here. There's a Traminer function secdef. I can click on it, and this help page will give me the information about the usage and the information about how to specify each argument of the command. So you have to explore a bit what happens there. Then there are some details where there's more of a verbal explanation of what the command does, some references and some examples to use the different functions. I go back to the chat. Your help page look very different. It might be depending on the R version you have.
Yeah, I was having trouble finding the part that listed the packages, kind of what we were first looking at. Mine looked different, but once I searched kind of using that upper search box, it was fine and the packages popped up. So
okay.
Yeah, thanks.
Sure. Okay, maybe I can anticipate something here while we wait. The code we're going to use today is let's say a summary of the code that together with Marcel Rab, we prepared for a book that is coming out hopefully in May by Sage, which is an introduction to sequence analysis. So I don't want to make too much of an advertisement here, but is to especially highlight that together with the book, we generated a very rich companion page where you will find more code that what we can discuss together today that cover the basic steps of sequence analysis that we're going to introduce, but also broaden a bit the perspective on some of them. The good thing for you is that we use the same data that you are going to use for this workshop. So you can start to become familiar with that, with the two codes we share today, and then test further other options, looking at the code that we share in the companion page of the book. Of course, many of the explanations are in the book, not in the companion page, but the code and many other examples with figures and tabulation and
I'm just thinking, Emanuela, you could also post the link to our Dropbox where the data is in there here.
Here we are. You should be able to download all materials from this link. So when you download the folder, you're probably in this situation now in part 2. As I said, what I recommend is to link on this essay part 2 our project, because then everything we do will happen within this folder. And it's gonna be easier to store things and save figures, etc. All right. So here we are. We start with this R code SA part 2. What we start to do is to load the packages we need. So I already see that some of you might have some issues loading the packages. I hope this will not happen actually, but we'll see. What you do to run the code is you can either select it and use the run button here on the top, or use a shortcut, which might depend on your computer. So what I do is to load my packages. And what we see here is that R is working a bit and is telling me what packages is loading and what are the main names of the functions there. I now want to import the data. So Annette showed you before that if you go to the data folder, you see this partner bio DTA. So this is a data file. What we do is to import it directly in R using the read DTA function. And here we are using additionally this here function, which comes from one of the packages we loaded before, which basically says R, well, look at the environment we are working on, which we see here on the line on the top of the console, which is part 2. Look into the environment, go into the data folder and upload the DTA file that is called partner bio, BERT bio DTA, and store it in my working environment as a file called family. If I run this, I see that here in the environment, there's this new object, which is the data I uploaded, which contains 1,866 observation individuals and 2,081 variables, my columns, where the information about the sequences are stored. So out of this data set, we now define the sequences, but we need to know where the sequences start in my data and where they end, and especially the names of the variables that we are using there. So I see that using the names function and specifying the family object, R returns me a number of labels, which is the names of the columns. And I see that columns are named from state 1 to state 264, and there are other variables like sex, life satisfaction, education, etc. So I want to identify where the sequences start and where they end. I can use the match function. And in this case, R will tell me that the state 1, which is the first data point, is in column 18, and state 264, which is the last, is in column 281. And I use this information to generate my sequences later on. All right, what do I do before actually using the secdef function is to identify the states, so the alphabet that I'm going to use. And for this, I have to create some labels. I use short labels, like in the figures I showed you before, single with children, LAT with children, etc. But also long labels. And long labels are already stored in my data. In fact, if I look at one single column, which is state 1, I see that the values of that column are single, no child, single, children, etc. So I just use this information, extracting the label with the $ function, and generate out of this the long labels that I'm going to use later. You see that as I generate objects, also my environment here gets richer. I not just don't have the family, but also some values. I have the short label and the long label I just generate. Okay, but I also want to generate colors. In this case, I use the Brewer function. I show you here how to display the color of a specific element of the palette. What I do here is to select different colors from different elements of the palette. So I use the Brewer pal function to extract, using this flag, to extract from this object 3 elements of the blue element of the palette from 2 to 3. And I generate an object that is called col1, color1, just with these values. And here you see that my environment has now a col1 object, which is a combination of two elements, which are the codes referring to two colors. I do that for other 3 sets of colors. And then I combine them together using the concatenation function C. And I generate an object which concatenates all the information that I extracted from the brewer file. How does it look like? Like this. So you can play around changing colors, testing your combination. So now I have also a color object. Finally, we get to the secdef function, which is the core of this session. The secdef function generates an object that I call family month sec, because we have monthly data here. And what it does is to take the family data set, select column 18 from column 18 to 81, sorry. Label the states using the short label I generated. Indicated the long labels using the long labels we just generated, extracting them from the initial data. Attaching the colors that I just selected using the cfal option. In this case, I do use weights. I have to specify where the weight variable is stored. It's stored in the family data, which is the place where sequences come from. And then I identify which are the identification number for each individual, which is stored in the variable ID belonging to the family data set. And in this case, I also say, well, okay, you have many months. These are like around 200 something. Specify at what time intervals you put the tick marks that will be used for visualization later. What do I do here? I select my secdef, I run it. It will take some time, but then R will tell me that it generated a sequence object that has these labels, short and long, and contains 1,866 sequence with the same length. So that's, you already have your sequence objects here stored in your environment. But now what we want to do is to move from yearly to, from monthly to yearly. If you want to learn more about what to, how to store your data in different formats, you can explore different functions such as the sec format. And here we use the sec granularity function with Intraminer to move from monthly data, the sequence object we just generated, to yearly data, another sequence object specifying the temporal span. So I want R to extract the most frequent state among the 12 for each year and define it as the state of the year. And if I run this, I obtain an object with some time that in fact has the same number of individuals of observations, but has less variables simply because we move from months to years, from 164 months to 22 years. All right. I want to display some of the sequences. This is just to reproduce what Annette showed you in the first session. So the state sequence format, the distinct successive format for one selected sequence, which is number 8 in our sample, it's just a random sequence, and the state permanence format. So this is specifying the state and the duration. Can you do this for all sequences? Not really. So this is just for you to know how to explore the data, but you rather want to use those functions we had a look at on the slide. So you want to know what is the mean time spent in each state. You will get with the segment function a very brief summary of what's going on in your data. You want to know what is the proportion of time in each state. So we know that 24% of the months here are spent in singleness, that 2.6% of the months are spent in singleness with children, and so on. The same applies to the SEC DSS, so the number of episodes. And here you see that you can learn already a lot about your data by looking at this summary measure. Number of transitions look pretty much the same. So you can do it for months and for years, and you will see that you will get the different numbers exactly because the variation in monthly data is large. I will not go through the transition metrics, not to steal too much time for this. What I want to highlight is that all the tables that you can display in your console can be stored and exported as a CSV file if you want to manipulate them and use it for your own papers or for summary tables. How you do that? You use the write CSV function. You can like test it yourself with your data, and you will see that everything that you generate here and store in the CSV can be stored in your, for example, table subfolder. All right. I want to show you one type of visualization for each representative of the two types. So the visualization as a summary visualization or as a individual sequences of visualization. We have seen before the model plot. So what happens here is that we focus on these three lines. The SEC-MS plot is the command to display the model plot. Important here, if I don't know what plots are available, I type into the help SEC plot, and TraMiner will tell me here that there are this many plots I can explore. So you see that there's more variation than what we can discuss together today, but to stick to what we have seen already and you are familiar with, the SEC-MS plot will return you this combination of men and women model plot over time. Here we specify our sequence object, and we tell R that we want them to be grouped by the variable sex that is stored in the dataset gender. I have to specify border and A, because otherwise R will put a vertical line at each time point, and this is very disturbing when you plot something there. So here you see in the plots that we have already this result, but there are some flaws. The labels are not really visible. The legend is very bad. Unfortunately, this is not possible to fix here, because what we want to do is to store this figure on our machine. So we use the PNG function, and we tell R, well, store it here in the figures subfolder, call it model plot base color, give a figure a certain width and a certain height, and then close the visualization. If I run this whole section of the code at once, and then I go to my folder and look at hands-on part 2 figures, here I am with my figure, and at least here the labels and the legend is visible. So now you know how to store also figures on your machine from what you generate here. But let's consider also the distribution plot. So this overall picture, the SECD plot is the command, the input is the same, and I give a title to it. The main title is yearly granularity. And here you have already your figure, but you see that also here the legend is not great. So you might want to store it again on your machine. And on the code, you will see how to do that. Of course, you can do the same as we did for the model plot, also for the distribution plot, and ask TraMiner to plot it for the two groups, men and women, in our data, specifying the group function. And already here, we have some information. We can learn, for example, what we were discussing before, that there's more or less the process look the same for men and women, but for women is a bit anticipated at the beginning of the life course. So this tells us that women move earlier in their life course into specific state, but the general process look the same for the two groups. All right, and we conclude with the index plot. the command is in this case sec_iplot, and it will take a little bit of time to plot this because it's not a summary of the states at each time point, but it's really plotting each and every sequence, 1,800 in our pool of sequences. So you will see that it will take some time as you experience. And you also see that it's very messy. And as I told you before, probably there's some overlapping, not ideal to learn about what's going on there. One thing that we can start to fix is to order the sequences according to some criterion. And here we order it from start, sort V equal to from start, which means from the first to the last episode, according to the order of the legend. Is this substantially meaningful? Not really, maybe. You can find out whether for your research question, there are other sorting criteria. And in the extra code I mentioned before that you can find on the companion page of the book, you will also find some of the extra code for doing this. So you see that here, at least we have a better picture. We see that many individuals are in singleness, and the proportion of being single decreases over time. And we see a lot of purple at the end, so probably many people are married, but still this representation is not super reliable when we want to learn about the unfolding over time for individuals. All right, so I will conclude here with the last command, because what we have done so far, so generating the sequences and storing the data, generating the labels, can be saved for a future usage. What we do is to save an image, an R data file, and I store it in my data folder here, so that when I go back to my data folder, I see that there's not just the DTA, but also this environment that I just generated with the sequences, and we can use it for the next session. Okay. No, when you share, stop share. I guess there are some questions about the code in the chat. It's hard to address all of them. So for those who couldn't really reproduce at the same time as I was running the code, I suggest that you take a little bit of time and you try it yourself. And if you really don't manage to run it on your machine, you get in touch with me via email, and I'm happy to follow up on this. Annette.
Yeah, I'm still trying to answer some here, but yeah,
okay.
I would also say take your time. Some of these things with the installations might have to do with your computer and admin rights and so on. Also backward and forward slashes, depending on whether you're on a Mac or Windows machine, are also a common source of headaches. There was one about the input here. So we're using the package Haven here in the example, but there's another package called Rio, an import package that's also good to import data, data sets. I would say for now, let's have a break, 15-minute break.